Welcome to The Explainer. Today, we're going to tackle a question that honestly seems to defy all logic. A puzzle that plays out every single time you sit around a campfire.
So let's just dive right in, shall we? Picture this. You've got a heavy log, right? Pounds of wood. You burn it, and when the fire dies down, all that's left is this tiny little pile of ash that weighs practically nothing. It really feels like a magic trick, doesn't it? Like poof, the matter just vanished. But did it really?
Here's how we're going to crack this case. We'll start with the fire itself, then get into two different kinds of changes before we uncover matter's golden rule. After that, we'll learn to spot the clues, see what the atoms are really up to, and finally figure out what it takes to get the whole reaction started.
All right, first up, the mystery of fire. This whole process we call combustion, it's kind of like the perfect crime scene, right? It looks for all the world like matter is being completely destroyed. But, as you're about to see, science tells a totally different and way more interesting story. Okay, so to really get to the bottom of this, our first big clue is understanding that not all changes are created equal. There's a huge difference between something just looking different and something becoming fundamentally different. And this is where it gets really clear. On one side, you've got a physical change. Think about melting ice. It goes from a solid to a liquid, but it's still just water, H2O. Its identity hasn't changed. But a chemical change? That's a whole other ballgame. When you burn wood or when iron rusts, you are literally creating new substances. The original stuff is gone, replaced by something completely new.
This brings up a couple of key terms you gotta know. The stuff you start with, the log and the oxygen from the air, we call those the reactants. And all the new stuff that gets made, the ash, the smoke, the gases, those are the products. Reactants turn into products. It's a complete chemical makeover.
So this whole idea of reactants becoming products, it leads us straight to the single most important rule in our entire investigation. I mean, this principle's the key to everything.
And boom, here it is, the law of conservation of mass. In a nutshell, it says that matter can't just be created out of thin air, and it can't be destroyed. It can only change form. So that mass from the log, it didn't disappear, it just put on a different costume. The total weight of all your reactants must equal the total weight of all your products. No exceptions.
So why does it look like the mass is gone? Well, this slide explains it perfectly. Your campfire is an open system. All that smoke and gas, which has weight by the way, just floats away into the atmosphere where we can't measure it. But what if you could burn that same log inside a giant, perfectly sealed container? A closed system? If you weigh that whole setup before and after the fire, you know what you'd find? The scale wouldn't have moved one bit. The weight would be exactly the same.
All right, so we get it for the log. It's a chemical change. But how can you be a chemical detective in your own kitchen or garage? What are the telltale signs that a chemical reaction is actually taking place?
Well, you look for the clues, the fingerprints of the reaction. A change in color, like when a shiny nail turns to reddish-brown rust, that's a big one. A change in temperature that happens all on its own, a new smell, bubbles fizzing up. All of these are dead giveaways that a chemical switch has been flipped and new products are being made.
Okay, so we've solved the what happens. Mass is conserved. But now for the how. How does this actually work on a microscopic level? If no atoms are ever destroyed, what in the world are they doing to create completely new things?
And here is the big secret. It's not magic at all. It's just a shuffle, a grand atomic shuffle. Think about it. The universe isn't making new atoms from scratch or making old ones disappear. It's just working with the same set of atomic building blocks, rearranging them into new patterns and structures.
It's really like a molecular square dance. First, the bonds holding the original molecules together have to break. That's the dancers letting go of their partners. Then, the atoms all rearrange, shuffling around the dance floor. And finally, new bonds form, creating the products as they all grab new partners. Same dancers, just a totally new dance formation. And if you need proof, just look at the numbers. Here's the recipe for making water. On the reactant side, you start with 4 hydrogen atoms and 2 oxygen atoms. Now look at the products, the water molecules you've made. How many atoms? 4 hydrogens, 2 oxygens. It's exactly the same number. They've just been rearranged. Nothing was lost. The books are perfectly balanced.
We are on the home stretch. We know atoms have to rearrange to make new things, but they don't just decide to do it on their own. So what's the trigger? What does it take to get this whole atomic dance started?
Well, it turns out it all comes down to collisions. It's not enough for the reactant molecules to just be in the same room together. They have to physically crash into each other. And not just any little tap will do. They have to collide with enough force and at just the right angle to actually break those old bonds and start the shuffle.
And that initial jolt of energy they need, that's what we call activation energy. It's the spark. It's the match you use to light the log. It's that minimum push needed to get over the energy hump and kick the whole reaction into gear. Once it gets going, a reaction like fire can often produce its own energy to keep the chain reaction alive.
And that brings us all the way back to our campfire. The mystery is officially solved. The mass of that log didn't vanish into nothing. It was transformed, perfectly following the law of conservation of mass. It became that little bit of solid ash, plus a whole lot of smoke and invisible gases that just floated away. If we could capture every single particle, the total mass would be exactly what we started with. It's all still there.
And this idea, this fundamental rule that matter is never lost, only rearranged, it is absolutely mind-blowing. It means the very atoms that make up your body right now have existed for billions of years. They have been parts of stars, rocks, maybe even dinosaurs. So that leaves us with one final big thought to chew on. If everything we see is just a new arrangement of the same old atoms, what else can they become? What amazing new combinations are still out there, just waiting to happen?